Hello everyone. In this video, we shall discuss how to solve exponential and logarithmic equations. So first, let us deal with solving of exponential equations. The key concept in solving exponential equations is to know the laws of exponents that you learned in algebra. So first, let A and B be any positive real numbers that are not equal to 1, and let X and Y be any real number. So the first rule of the laws of exponents would be whenever we have A raised to X times A raised to Y, then the product of these two will be the base A raised to the sum of the exponents X and Y. For rule number 2, if we have A raised to X over A raised to Y, then this quotient is equal to the base A raised to the difference between the exponents X and Y. Now for rule number 3, whenever we have A raised to X and then again raised to Y, this expression is equal to the base A raised to the product of these two exponents. And then for rule number 4, if we have A times B raised to X, then we can distribute the exponent over multiplication, and then we get A raised to X times B raised to X. Now for rule number 5, A over B raised to X, this means that we can distribute the exponent over division. So therefore, we get A raised to X over B raised to X. Now another key concept in solving for exponential equations is the property of exponential functions, that is the one-to-one property. So the one-to-one property of the exponential function states that whenever we have A raised to X is equal to A raised to Y, then we can say that their exponents are equal. So in other words, if we are working on an equation wherein the left side and the right side have the same base A, then we can just simply equate their exponents. So for example, let us try to solve 2 raised to X is equal to 64. Now in this equation, in the left side, the base is 2, while in the right side, the base is 64. So in order to solve this by using the one-to-one property, we have to write 64 as a power of the base 2. Now 64 can be written as 2 raised to 6 because it is the product of 6 copies of 2. Now since this equation has the left side and right side having the same base 2, then we can simply conclude that the exponent x is equal to the exponent 6. So this is our solution for this particular equation. Now for another example, let's solve for 2 times 3 raised to x minus 2 plus 5 is equal to 167. For this equation, we need to transpose positive 5 from left side to right side. And so we get 2 times 3 raised to x minus 2 is equal to 167 minus 5 is 162. And then we will divide both sides by 2 so that this thing will cancel out. And then the left side will just be 3 raised to x minus 2. And then the right side is 162 divided by 2, which is 81. So this is actually similar to the equation that we had in the previous slide. So we shall write 81 as a power of 3. So 81 can be written as 3 raised to 4 because 81 is the product of 4 copies of 3. Now, since our equation has the same base for both left side and right side, then we can just simply equate the exponent x minus 2 and the exponent 4. And then transposing negative 2 to the right side, we get x is equal to positive 6. So this is our solution to this particular equation. Okay, next, let us try to solve for 64 raised to x is equal to 512 raised to x minus 5. So in the left side, the base is 64, while in the right side, the base is 512. Now, we can actually think of a common base for 64 and 512. Now, 64 is actually equal to 2 raised to 6, while 512 is equal to 2 raised to 9. So 64 can now be written as 2 raised to 6, and then this thing is raised to x, while 512 can be written as 2 raised to 9, and then this thing is raised to the exponent x minus 5. Now, applying the laws of exponents shown in the first slide earlier, we can just multiply the exponents in both the left side and in the right side. So in the left side, we have 2 raised to 6 times x, which is 6x, while in the right side, we have 2 raised to 9 times x minus 5, which is 9x minus 45. So since our equation has the same base now for both left side and right side, then we can just equate the exponent 6x and the exponent 9x minus 45. So transposing 9x to the left side, we get 6x minus 9x, which is negative 3x. And on the right side, we have negative 45. So dividing both sides by negative 3 to solve for x, we get x is equal to positive 15. So this is our solution to this particular equation. Let's have another one. Let's try to solve for 8 raised to 1 minus 2x times 8 raised to negative 2x minus 3 is equal to 8 raised to negative x. Now observe that in the left side, we have the product of two exponential expressions having the same base 8. So in this case, we can use the law of exponent a raised to x times a raised to y is equal to a raised to x plus y. So which means that this product can be written as a single exponential expression, but we need to add their exponents. So adding these two exponents, now we get negative 2x plus negative 2x is negative 4x. And then positive 1 added to negative 3 is equal to negative 2. And then the right side, we have 8 raised to negative x. So our equation now has the same base for left and right sides. So by the one-to-one property, we can just equate their exponents. So solving for x, we will transpose negative x to the left side and transpose negative 2 to the right side. So this gives us negative 3x for the left side and positive 2 at the right side. And then dividing both sides by negative 3, we get x is equal to negative 2 over 3. And this is our answer for this particular equation. Okay, another one. So let's have solve for 81 raised to 3y plus 2 over 243 raised to negative y is equal to 3 raised to 4. So if we observe in the left side of the equation, we have a quotient of two exponential expressions having the base 81 and base 243. In the right side, the base is equal to 3. So the common base for 81, 243, and 3 is 3. So which means that we have to write 81 as a power of 3 and 243 as a power of 3 as well. So 81 can be written as 3 raised to 4. 243 can be written as 3 raised to 5. So in this case, 81 will now be written as 3 raised to 4. And then this thing is raised to the exponent 3y plus 2. And then in the denominator, 243 will now be replaced by 3 raised to 5. And this thing will be raised to negative y. And then the right side will remain the same, it's 3 raised to 4. So applying the law of exponent, a raised to x raised to y, this will be equal to a raised to the product of x and y. So which means that in the left side of the equation, the numerator now will have 3 raised to the product of 4 and 3y plus 2, which is 12y plus 8. while in the denominator we have 3 raised to negative 5y. And then the right side will still remain the same as 3 raised to 4. Now, in the left side, this is now in the form of a raised to x over a raised to y. So again, using the laws of exponents, we can write this as a single base a raised to the difference between their exponents, x and y. So which means that this left side can be written as 3 raised to 12y plus 8 minus negative 5y is equal to 3 raised to 4. So simplifying the exponent in the left side, we get 3 raised to 12y minus negative 5y is positive 17y. And then we have plus 8 is equal to 3 raised to 4. So since our equation now has the same base 3, then by the one-to-one property of exponential functions, then we can just equate their exponents. So this means that 17y plus 8 is now equated to positive 4. And then transposing 8 to the other side, we get 17y is equal to negative 4 because it's 4 minus 8. And then dividing both sides by 17, we get y is equal to negative 4 over 17. So this is our solution for this particular equation. Okay, next. So let's try to solve for e raised to x squared minus 5x equal to 1. Now remember or recall that e is the natural exponential number which is approximately equal to 2.71. So in order to solve this equation, we can write this value in terms of e raised to something. So we know that e raised to 0 is equal to 1. So we can replace this by e raised to 0. So we get e to the x squared minus 5x is equal to e raised to 0. Now, since this equation has the same base e for both the left and the right side of the equation, then we can use the one-to-one property by just equating the exponents x squared minus 5x and the exponent 0. So this one is a quadratic equation in x. So we can factor out the common factor x. And then the second factor will be x minus 5. So equating both factors to 0, so we have x is equal to 0 and x minus 5 is equal to 0. So this means that when we transpose negative 5 to the other side, we get x is equal to 5. So the solutions are x equals 0 and x is equal to 5. Now, for logarithmic equations, and the key concept is to know how to convert a logarithmic expression into its corresponding exponential form. So we know from our previous videos that y equals logarithm of x to the base a is a logarithmic equation. And then we can actually convert this into its corresponding exponential form by getting the base and then raising it to this value y. So this thing will become the exponent. And that exponential expression must be equal to the parameter x. So that's why we have a raised to y is equal to x. So this is one key concept in solving for logarithmic equations. Now, another key concept in solving for logarithmic equations is the one-to-one property of logarithmic functions. So the one-to-one property of logarithmic functions states that whenever we have the logarithm of x to the base a and it is equal to the logarithm of y to the base a, then we can just equate their parameters x and y. So we can only do this whenever we're using or whenever we see logarithms of the same base a. And then another key concept in solving for logarithmic equations is to know how to use the laws of logarithms. So if you recall that in the laws of logarithms, whenever we have the logarithm of a product, then we can split it as a sum of the logarithms of each factor. And then for rule number 2, whenever we have the logarithm of m over n, we can split it as the difference of the logarithms of the numerator and the denominator. And then rule number 3, whenever we have the logarithm of m raised to an exponent c to the base a, then we can write the exponent c as a multiplier of the logarithm. Now, the following rules are just similar to the first 3 rules, as we only use these green colored rules whenever the base is equal to 10. And then the last 3 rules here, we use this whenever the base is equal to the natural exponential number e. So let's try to use these key concepts in order to solve for the given logarithmic equations. So let's solve for the logarithm of x squared minus 6x to the base 3 is equal to positive 3. So since this equation contains a logarithm or a single logarithm at the left side and a constant at the right side, then we have to convert this into its exponential form. So we have to convert to exponential form. So to convert this exponential form, we get the base 3, the base of the logarithm, and then we raise this using this constant value at the right side, and then equate it into the parameter x squared minus 6x. So simplifying 3 raised to 3, that's going to be 27, is equal to x squared minus 6x. Now, transposing 27 to the right side, we get 0 is equal to x squared minus 6x minus 27. Or we can write this as x squared minus 6x minus 27 is equal to 0. So since this is a quadratic expression, we will use either factoring or completing the square or quadratic formula. But since this is factorable, we can factor this as x minus 9 times x plus 3 and equate to 0. And then equating both factors to 0 and solving for x, we get x is equal to positive 9 and x is equal to negative 3. However, we have to be careful whenever we're dealing with logarithmic equations, because we know from the discussion of the logarithmic functions that the domain of the logarithmic function must be all real numbers that are positive, or whenever the parameter is greater than 0, because we cannot have a logarithm of a negative number. So we have to be assured that the parameter inside must be a positive number. So which means we need to check. Okay, so we need to check if x equals 9 will make this a negative number, and check x equals negative 3 if that will make this a negative number. So if we will substitute x equals 9, if x is equal to 9, we get 9 squared minus 6 times 9. So 9 squared is 81 minus 54. So that's going to be positive 27. So that's okay. So that's allowed. So x equals 9 is a solution to this particular equation. Now, if we use x is equal to negative 3, we have negative 3 squared minus 6 times negative 3. This will give us positive 9. And then negative 6 times negative 3 is positive 18. So we get positive 27. So again, since this is positive, then x equals negative 3 is allowed to be a solution of this equation. Okay, next. Now suppose that we have an equation, a logarithmic equation, wherein the left side and the right side contains a logarithm of the same base. So in this case, we have a logarithm of the same base 2. So in this case, the key concept that we can use is the one-to-one property of logarithmic functions. So that means we can just equate the parameters 2x minus 3 and the parameter x plus 4. And then we solve for for x. So transposing x from right to left side, we get 2x minus x is equal to x. And then transposing negative 3 to the right side, we get 4, and then plus 3 is going to be 7. And again, we need to check if this x value will make each of these a negative number. Okay, so if we try to substitute 7 here, 2 times 7 is 14. 14 minus 3 is positive 11. So x equals 7 is okay for this logarithm. And then whenever we have x plus 4 as parameter, so we have 7 plus 4 is positive 11. So also this is okay. So which means that x equals 7 is a solution of this equation. Okay, next. Now this time let's try to solve for the logarithm of 3x minus 5 to the base 7 plus 8 is equal to 10. So we have a logarithm at the left side, and then there's a constant added to it. So which means in order to solve this equation, we will transpose first the positive 8 from left side to right side. So we write this as the logarithm of 3x minus 5 to the base 7. And this is going to be 10 minus 8 is positive 2. And then since we have a single logarithm equals a constant, then we have to convert to exponential. Okay, so 7 square, so the base raised to this number is equal to the parameter 3x minus 5. So 7 square is 49, and then 3x minus 5. Negative 5 will be transposed to the left side, so it's going to be 49 plus 5, which is 54, is equal to 3x. And then dividing both sides by 3, we get x is equal to 18. So before we declare this as a solution, then we have to check first this particular parameter. So 3 times 18 is 54, minus 5 is positive 49. So x equals 18 is okay for this particular parameter. So that means x equals 18 is a solution of this equation. Okay, next. Now this time we have logarithm of x to the base 4 minus the logarithm of x minus 1 to the base 4 is equal to 1/2. So if you observe in the left side, it's a difference of two logarithms. So we know that there's a logarithm rule that we can combine this difference of two logarithms as a single logarithm. So if we recall, if we have logarithm of m to the base a minus the logarithm of m to the base a, we can write it as the logarithm of m over n to the base a. So which means the left side here can be written as the logarithm of x over x minus 1 to the base 4 is equal to 1/2. Okay, and then since we have a single logarithm equals a constant, then we have to convert this into its exponential form. So that's going to be 4, which is the base, raised to the number 1/2, and it's equal to x over x minus 1. Now 4 raised to 1/2 is square root of 4, which is equal to positive 2. So this thing is positive 2 equals x over x minus 1. And then we multiply both sides by the LCD, which is x minus 1. So the left side now will be 2 times x minus 1, which is 2x minus 2. On the right side, we cancel x minus 1, and we write x. Now x will be transposed to the left side, and negative 2 will be transposed to the right side. So thus we get x at the left side, and then positive 2 at the right side. But of course, before we declare if this is a solution of the equation, then we have to substitute it in the parameters. So if x is equal to 2, this is positive, and then 2 minus 1 is positive 1, that's also positive. So which means x equals 2 is a solution to this particular equation. Okay, next. So now for This particular equation, we have the logarithm of x minus 2 minus the logarithm of 2x minus 3 is equal to the logarithm of 2. So in the left side, it's the difference of two logarithms. So just like what we did in the previous example, we will write this as a single logarithm, and then we get the quotient, x minus 2 over 2x minus 3. And then we rewrite the right side, which is just logarithm of 2. Now, since this equation has logarithms in both the left side and the right side, and both of them have the same base, which is 10. So using the one-to-one property of logarithmic functions, then we can just equate the parameters. So equate the parameter x minus 2 over 2x minus 3 and the parameter 2. So multiplying this or both sides of this equation by 2x minus 3, we get x minus 2 for the left side because 2x minus 3 will cancel out. While at the right side, we have 2 times 2x minus 3, which is 4x minus 6. And then solving for x, we transpose 4x to the left side, so we get negative 3x. And then transposing negative 2 to the right side, so we get negative 4. So dividing both sides by negative 3, then we get x is equal to positive 4 over 3. However, if we check 4 over 3 here, 4 over 3 minus 2 is negative 2/3. So which means that there will be a problem in this parameter. Okay? So which means that we cannot use this value of x for this logarithm. So now, in that case, our equation here doesn't have a solution. So this one is not a solution of the given equation because it violates the positive property of the parameter. So which means that this equation has no solution. Okay, next. This time we have the logarithm of x to the base 6 plus the logarithm of x minus 9 to the base 6 is equal to positive 2. So if you observe that in the left side, we have the sum of two logarithms. So we can combine this as a single logarithm using the property stated earlier that whenever we have the logarithm of m to the base a plus the logarithm of n to the base a, then we can combine them as a single logarithm of the same base a, but the parameter will be the product of m and n. So in this case, combining these two logarithms into a single logarithm, we write it as the logarithm of x times x minus 9 to the base 6. And we equate it to the constant 2. So now since our equation contains a single logarithm at the left side and a constant at the other side, then we have to convert this into an exponential expression. So the base is 6, and then we have to raise it to 2, and then equate it to x times x minus 9, which is x squared minus 9x. Now 6 squared here is 36, and then we have x squared minus 9x, and transposing 36 to the other side, we get 0 is equal to x squared minus 9x minus 36. And then, since this is a quadratic equation in x, now we can factor this as x minus 12 and x plus 3. So equating both factors to 0, we get x is equal to positive 12 and x is equal to negative 3. So if we check for x equals 12, so 12 will fit in this parameter because that's positive. And then 12 minus 9 here is 3. It's also positive. So which means that x equals 12 is a solution of this equation. However, the x equals negative 3 when replaced to x, then we will have a problem here because this will become logarithm of a negative number to the base 6. So x equals negative 3 is not a solution. So for this equation, the only solution is x is equal to 12. Okay, and then for another equation, we have ln of 6x minus 5 is equal to 3. So this one is a logarithmic expression equated to a constant. So again, we have to convert this into its exponential form. But this one has base e. So the base here is e. So converting this into the exponential expression, we have the base e will be equated to 3. The base e will be raised to 3. And then we're going to equate it to the parameter, which is 6x minus 5. So solving for x, we shall transpose negative 5 to the left side and write e raised to 3 plus 5 is equal to 6x. And then dividing both sides by 6, we get x is equal to e raised to 3 plus 5 over 6. Now, to check if this will be an allowed value for 6x minus 5, so 6 multiplied to e raised to 3 plus 5 is over 6 will be e raised to 3 plus 5. And then if we subtract 5 from this thing, that's going to be e raised to 3. Now, since e is a positive number, and when we raise it to 3, it will also be a positive number. So there will be no problem in the parameter of ln. So which means that this is our solution to this equation. Okay, and then we move to the other exponential and logarithmic equations. So for instance, if we have the equation 5 raised to 3 minus 2x is equal to 6 raised to x plus 5. Now, in the left side, the base is 5. In the right side, the base is 6. And there is no way of writing the base 5 as a power of 6. And there's no way of writing the base 6 as a power of 5. So if we have this kind of exponential equation, then we have to apply logarithms to both sides of this equation. Now, there are many ways to do that. So we can actually use the common logarithm. So when we say common logarithm, it will be base 10. So if we're going to apply logarithm of 5 raised to 3 minus 2x is equal to the logarithm of 6 raised to x plus 5, applying the law of logarithm wherein we bring down the exponents, then this will give us 3 minus 2x times the logarithm of 5 is equal to x plus 5 times the logarithm of 6. And then distributing the logarithms to the expressions or to the terms inside the groupings, then we get 3 logarithm of 5 minus 2x logarithm of 5 is equal to x times the logarithm of 6 plus 5 times the logarithm of 6. And then we group all the terms that contains x. So in this case, we can transpose this negative 2x logarithm of 5 to the right side and then transpose the 5 logarithm of 6 to the left side. So we get 3 logarithm of 5 plus 5 logarithm of, minus 5 logarithm of 6. So this is minus 5 logarithm of 6 equals x logarithm of 6. And then this thing here will become positive 2x logarithm of 5. Okay. And then factoring the x in the right side, we get x times the logarithm of 6 plus 2 times the logarithm of 5. And then in the right side, we have in the left side, we have 3 logarithm of 5 minus 5 logarithm of 6. So dividing both sides of this equation by this thing, we get x is equal to 3 logarithm of 5 minus 5 logarithm of 6 over logarithm of 6 plus 2 times the logarithm of 5. So using some laws of logarithms, so we can write this as x is equal to the logarithm of 5 cubed over 6 raised to 5. And then over this thing can be written as the logarithm of uh, the logarithm of 6 times 5 raised to 2. So that's how you simplify it. No? That's how we simplify using laws of um, logarithms. Now, the other ways to solve this particular equation is to use the natural logarithm. So instead of applying logarithm or common logarithm to both sides, we write ln of the left side and ln of the right side. Now, also, we can use logarithms of base 5 and logarithms of base 6. However, if we apply, let's say, if we're going to apply logarithm to the base 5 for 5 raised to 3 minus 2x, then this thing will just become 3 minus 2x. No, it's another property of the logarithms discussed in the previous discussions. Okay, so I will not show this anymore in this video, but you can maybe try this out, no, whenever you have a free time. Okay, now let's move to the next one. Let's try to solve for e raised to 2x minus 5 e raised to x plus 6 is equal to 0. Now, this particular equation is actually quadratic in format. So when we say quadratic in format, we can let m to be e raised to x. So that means we're going to replace this by m. And then since e raised to x is equal to m, then e raised to 2x will be m squared. So that implies that when we square m, it's going to be e raised to x squared, which is e raised to 2x. So that means e raised to 2x can be replaced by m squared. So which means our equation now will become m squared minus 5m plus 6 is equal to 0. And then factoring this, now we get m minus 3 times m minus 2 is equal to 0. And then equating both factors to 0, we get the following. And then solving for m, we shall get m equals positive 3 and m equals positive 2. However, m is equal to e raised to x. So we have to replace m by e raised to x. And then solving each of these equations, now we can solve for x by applying ln of both sides. So ln of e raised to x is equal to ln of 3. ln of e raised to x is equal to ln of 2. So applying this ln will cancel out with e. So we get x is equal to ln of 3. And then for the other equation, ln and e will cancel out. So the left side will be x. And then the right side is ln of 2. So our solution will be x equals ln 3 and x is equal to ln of 2. Okay, next. Now, how about whenever we have a logarithmic equation having this format? The logarithm of the logarithm of x to the base 3 to the base 2 is equal to 2. So first, we are going to convert this equation into its exponential form using the first logarithm. So the base here is 2. So that's going to be 2 squared is equal to this parameter, which is the logarithm of x to the base 2. And then 2 squared is equal to 4. And then we just rewrite the right side. And then this one is a logarithm equals a constant. So again, we write this as base raised to 4 is equal to the parameter x. So x here is equal to 3 raised to 4, which is 81. Now 81 is allowed here because 81 is positive. So which means that x is equal to 81 is the solution of this particular equation. And then finally, whenever we have this type of logarithmic equation, now let us solve for the square of the logarithm of x to the base 3 minus 3 times the logarithm of x to the base 3 plus 2 is equal to 0. So just like in the other exponential equation earlier, this is treated as a quadratic equation. So we can actually let m to be the logarithm of x to the base 3. So that would imply that m squared is equal to the logarithm of x to the base 3 quantity squared. So which means that this thing here will be replaced by m squared. This thing here will be replaced by m. And so our equation will now be written as m squared minus 3m plus 2 is equal to 0. So factoring this particular quadratic equation, we get m minus 2 times m minus 1 is equal to 0. And then equating both factors to 0, we have m minus 2 equals 0 and m minus 1 equals 0. So this gives us m is equal to positive 2 and m is equal to positive 1. However, m is logarithm of x to the base 3. So we shall replace that by logarithm of x to the base 3 and equate it to 2. And then this one is again replaced by logarithm of x to the base 3 and then equate it to 1. So to solve for x, we will write this in exponential form. So that's going to be 3 squared is equal to x. And that's going to be 9 is equal to x. Now for the other equation, we have to write this as 3 raised to 1 is equal to x. And that's going to be x is equal to positive 3. Now since both of these solutions are positive, there wouldn't be any problem for the parameters x here. So which means that both of these are solutions of this particular equation. So this ends our video about solving for exponential and logarithmic equations. So I hope that you learned on how to solve the different types of these equations. And please do not forget to subscribe to my channel. Thank you for listening.